Have you ever stared at the clock in class and felt as though time was passing incredibly slowly? You can hear the teacher continuously presenting information, and when you glance around, everyone else looks immersed. It seems that you're the only one who feels the seconds dragging on, while time is moving normally for others. If you think your perception of time is altered, you're not very far off. Although you won't see this phenomenon in the classroom, relativity, general and special, explains when this actually happens. You might have heard of 4D as a cinema experience, with 3D glasses and moving chairs, wind, and light effects. It's the idea of something further than the normal three dimensions that we know, which can be modeled using the x, y, and z axes, representing length, width, and height. But what if I told you that 4D actually is a real thing, and that it's our reality? Previously, people used to believe that space and time are separate, that space is just this 3D entity in which things occur, and that time is independent of it, that it was a universal experience passing at the same rate everywhere. That these were the assumptions that Newton operated under. However, time isn't absolute. Its passage can be altered and affected by motion and gravity. It is relative to its frame of reference, to the observer's viewpoint. In space, we can move left and right, forward and backwards, up and down. Something is dimensional once there is movement across it. And time? Well, we move forwards in time. Therefore, our reality is composed of length, width, height, and time. Our reality is four-dimensional. Space-time. The main impacts of time being a dimension is that we experience time dilation, as per special relativity, as well as gravitational time dilation, as per general relativity. Within special relativity, the faster you move, the slower your own time runs compared to someone at rest. Meanwhile, in general relativity, the closer you are to a massive object, such as a planet or a black hole, the slower time passes for you. We'll get back to that in a second. Special relativity is a theory that revolves around two principal statements: that nature's laws are the same for all inertial frames of reference, and that those laws can help us calculate the constant value of speed of light within a vacuum, as applicable in all inertial frames of reference, regardless of the observer's perspective. It is important to note that relativity as a whole is based on the relationship between space and time, and that objects fall within frames that can either be stationary, such as the inertial, and moving, and their relation relative to the observer changes the perception we have of it. Then we have the Michelson-Morley experiment. The experiment is based on emitting light in two directions perpendicular to each other, measuring the speed at which they reach the screen. The hypothesis was that the speed of light constant relative to the hypothetical ether that the Earth was hypothesized to move through, and that there should be a difference between the values collected from each direction. However, when both values were identical regardless of the angle of the movement, this theory was disproved, and relativity was further proven. Then we have the Lorentz equation, which is the mathematical model for the changes in speed between a still and mobile frame. At the low speeds of day-to-day life, the value is so small that it is simple enough to be ignored. Meanwhile, as the speed approaches that of light, the value can increase and lead to an accurate perception of the changes. The gamma symbol represents the relativistic effects of a change in the positioning of the frame. And now, on to time dilation. However, we soon discovered that this was not the case. One way to picture the irregularities is sending an astronaut accelerating up to space with a light beam that they will shoot down. Both ground control that is monitoring the experiment, inertial, and the astronaut would report different times that the light beam reaches them. In the example provided, conditions are as far away from normal as can be experienced, and the difference can then be measured. The astronaut's measurements indicate a shorter period of time passing. That which is moving at a higher velocity is slower. Their clock moves slower compared to ground control. This can be due to a difference in speed or gravity. However, fundamentally, it centers around the geometry of spacetime. Another hypothetical experiment is taking a pair of identical twins and sending one off to space. By the time of return, the twin that remained on Earth will have aged more. This is known as the twin paradox. This paradox is then clarified as the traveling twin is moving between frames of acceleration and deceleration, which makes their experience asymmetrical to the twin on Earth. In theory, every time we take a journey, a readjustment of our watches and clocks must be made. However, on Earth, the effects are so slight that they are less than 1 millionth of a second. There is an equation in which 1 minus the velocity squared over the speed of light squared is square rooted in order to find the time dilation factor. The closer and closer v gets to c and that expression approaches zero, time almost stops for the astronaut. You might for a second think, Eureka! The secret to an infinite life. However, the astronaut's mind would have also stopped, so there is no benefit to the seemingly infinite lifespan. It's also important to note that only massless particles like photons can travel at c, the speed of light. To summarize this complicated concept, the faster you move through space, the slower you move through time. This disparity between perceptions was first detected within an experiment in 1977 at CERN, which involved a positive and a negative muon being shot across a loop. This confirmed time dilation, as when shot at a speed nearly equivalent to that of light, the lifetime of the otherwise unstable muons was extended by almost 30 times. Although that time that passed remained the same, the lifetime was prolonged as per our observations, despite the constant rate of decay from the particle's perspective. This reveals that the concept of multiple things occurring at once is conditional and depends purely on the observer. In the example of light being emitted from two different positions on a moving train at the same time, the observers will perceive it at the same time. But due to the movement of the observer on the train, that is not the case. Then we have the length contraction equation, which is also known as the Lorentz-Fitzgerald contraction. So, LO is the proper length of the object in rest or at a stationary frame. L is the contracted length. V is the relative velocity between the observer and the object. C is the speed of light. And as V is closer and closer to C, L becomes smaller and smaller, and when V equals C, the length would contract to zero. Why is that so? Well, when objects move faster, the geometry of space changes. It appears to contract in the direction of motion. This maintains the speed of light as a constant value. For example, a high-speed train passing by, theoretically seen contracting. However, that speed is insufficient for us to observe the length contraction. General relativity was first proposed by Einstein in 1915. It changed the way we view gravity. From a simple force acting at a distance, he demonstrated that it was more like an effect imposed by massive objects onto spacetime. If spacetime were a flexible sheet, massive objects such as the sun will curve it, and therefore alter the fabric of spacetime, so that objects with a smaller mass within a certain distance will eventually be pulled in. This was confirmed through the observation of the gradual Mercury shift, as, due to the perihelion, the point closest to the sun, is meant to slightly differ, if this is true, and as a whole, advance towards the sun. Small discrepancies within this pattern were then further explained by the general relativity due to the curvature, which also indicates a potential planetary crash. In addition to this, electromagnetic radiation is stretched within the gravitational field, resulting in redshift, otherwise known as the Doppler effect. We also predicted ripples in space-time that would be caused by two or more massive accelerating objects, such as two black holes colliding. This was then later detected in 2015, confirming the properties of space-time and the impact of masses upon it. In fact, there's a very well-known equation devised by Einstein that further explains his field theory. The left side explores the geometry of space-time, while the right side measures the matter and energy content. This part you can skip through. although it'll just be a brief explanation of what each of these terms means and why it supports his theory. The Ricci curvature tensor describes the curvature of spacetime locally, within a given area. Imagine a rubber sheet pressed downwards and curved. How much is curved is described by the Ricci curvature tensor. The Ricci scalar curvature multiplied by the metric tensor and divided by -2 represents the trace term, which ensures that the equation remains consistent in all frames, relating to the total scalar curvature. It is a scaled version of the metric tensor, with scalar multiplier across all frames. Basically, it ensures that there is always conservation of energy. Then there's the cosmological constant, which accounts for dark energy or vacuum energy, which makes this mathematical model applicable to an expanding universe. The right side considers the matter and energy content. Initially, it was meant to ensure a static universe. However, it was later found to support the expansion of the universe, therefore holding true as our understanding of the universe changes. It's almost a way of accounting for the universe's outward expansion, like the stretch of a balloon. This constant scaling factor ensures that the Newtonian gravity is accounted for, within appropriate limits. This ensures that within mathematical models, we can observe the curves within spacetime, even though they are imperceptible within our observations. Then there's the stress energy tensor. This contains all energy, mass, pressure, and momentum of said matter and radiation. Picture it as a map of all forces and energy flows within a region. It describes how much energy there is, how fast it's moving, and in which direction it's headed. All of this is considering a 4x4 matrix, a grid of numbers, which represent data and allow for transformations to occur within space. In addition to this, they also describe systems. We'll be covering these in a later video. Now, in normal English, the curvature of space-time is a direct result of the energy and momentum of matter and radiation within that given space. Now, there is one thing that doesn't quite fit in with general relativity: black holes. In general relativity, matter warps spacetime. However, this doesn't work with black holes, which are very dense points of matter, so dense that the curvature of space becomes so extreme that even light can't escape it. Approaching the black hole, general relativity is still applicable. However, at its very center, it's all a mystery. That specific point is called a singularity. Density is near, if not infinite, and no laws of physics as we know it apply. Everything is approaching infinity, with undefined behaviors and attributes. Einstein himself believed that black holes were too absurd to be real. But in 2015, we detected those gravitational waves mentioned previously, which were caused by two black holes colliding. These released 50 times more energy than all the stars in the observable universe, with each black hole measuring about 30 times our sun mass. The graph below shows the frequency, which is the sound as choreographed. Feel free to listen to it. This video is coming to an end. We've discussed how our reality is actually in 4 dimensions, general and special relativity, some experiments proving this, as well as how time and length are contracted within certain circumstances. We also took a sneak peek at a supporting equation, Einstein's field equation, which is actually a bunch of equations summarized to prove his finding. After a small touch on black holes, you may be left wondering, how much more do we still have to discover about physics and space? And the answer to that is infinity. Currently, there is a gap between relativity and other physics phenomena, such as black holes, and you may have heard about string theory and how it's a potential answer. We'll get back to that another day. Thank you so much for watching. Drop any topic recommendations in the form below and questions in the comments. I hope you've enjoyed enough to like and subscribe, and stay tuned for the next video. Have a wonderful day.